Hello, welcome to the wonderful world of physics. This is Physics 104, Chapter 15. We begin our study of fluid motion. And this video will cover Section 15.1, density and pressure. A fluid is defined as matter that flows under the influence of external forces. Now that can be liquids or gases. We are going to be looking at the motion of fluids, the behavior of fluids, the forces that act on fluids. And back during the first semester, when we were dealing with motion, we dealt with motion with a single object. Maybe it was a car, an airplane, a bullet, something like that. And we could use Newton's second law, F equals ma, and apply it to that bullet or car, whatever it was. But now when we think about a fluid, we're looking at many objects. In fact, in 300 milliliters of water, you've got 10 to the 25th power water molecules. Now, if we were to calculate the motion of every molecule, that would be a very burdensome set of calculations. The air in a room that's about 20 feet by 20 feet, there are 10 to the 27th air molecules. So it would be a great burden to calculate all the motions of those particles and how they interact with each other. But fortunately, we have methods of thinking about and quantifying the motions of fluids by using their macroscopic properties. Now, this means we're not going to be concerned with the individual motions and the forces of every individual particle, but rather we're going to look at the fluid as a whole. So we look at the macroscopic properties of the sample of fluid, so such things as pressure and volume and temperature and density. And you should get familiar with those letters. These are the variables that we use, P, V, and T. Density, we use the Greek letter rho. Let's talk about density. The equation for density of any substance, density is the mass divided by the volume. And so if you think about the units, mass over volume, that's going to be kilograms over cubic meters. Now some examples here. Water has a density of 1,000 kilograms per cubic meter. So if you picture a cubic meter of water, imagine a meter in length, in width, and in height, 1 cubic meter, and it has a mass of 1,000 kilograms. That means it would have a weight of 2,200 pounds. Other units that you might see with density are grams per cubic centimeter. So most often we in this class will be using kilograms per meter cubed because those are the MKS units, but you should also be able to readily convert to grams per cubic centimeter. So 1 gram per cubic centimeter. And you notice it's off by 3 orders of magnitude. So if you have kilograms per meter cubed and you want to know what that is in grams per cubic centimeter, just divide it by 1,000. So we get 1. Air is 1.28 kilograms per meter cubed. So picture that same cubic meter right in front of you, a meter in length, width, and height. The air in front of you, that's 1 cubic meter, it has a mass, 1.28 kilograms. Now I've written there, it says at STP, that means at standard temperature and pressure. Because as the temperature of a gas changes, as the pressure changes, it's going to have a different density. And we'll talk about that later on. But for standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere, there's the density of air. Aluminum, 2,700 kilograms per meter cubed. Divide that by 1,000, you get 2.7 grams per cubic centimeter. And gold is very dense. It is 19.3 times denser than water. So 19,300 kilograms per meter cubed, or 19.3 grams per cubic centimeter. You should know that a difference between gases and liquids is that gases are compressible. You put gas in a container and you can squeeze the container and the gas will change in density. And that was shown here. Air only has this density at a particular temperature and pressure. Liquids are incompressible, which means under forces trying to press it, it will not change in density. Now, everything has its limitations, and so if you put it under extreme pressure, it will condense. It will go to a greater density. However, under normal circumstances that we'll be dealing with in this class, we will consider that liquids are incompressible. There's a term you should know, specific gravity. It's a simple way of talking about the density of a substance. It is the ratio of a substance's density to the density of water. So for example, water, remember, has a density of 1,000 kilograms per meter cubed. Well, you divide that by its own density and you get 1. So water, by definition, has a specific gravity of 1. Aluminum, at 2,700 kilograms per meter cubed, you divide that by 1,000, you get 2.7. Or we could have just said 2.7 grams per cubic centimeter. Divide that by water's 1, and you get 2.7, and that's the specific gravity. So gold at 19.3 grams per cubic centimeter has a specific gravity of 19.3. It's just a simple way of talking about density. Notice that it doesn't have any units because specific gravity refers to a ratio, how much more dense this substance is than water. Let's talk now about pressure. Pressure is defined as force divided by area, and that particularly means the normal force applied to a surface divided by the area over which the force is applied. And in particular, in this chapter, we'll be talking about the pressure exerted by a fluid. However, a solid can exert a pressure as well. The units of pressure, again, think about the definition. It's force divided by area. So that's going to be newtons of force divided by area meters squared. And newtons per meter squared have a special unit to them, and that's called a Pascal. And the abbreviation is capital P lowercase a. When we think in this chapter about force exerted by a fluid, I want you to think about the air that's inside this balloon. And the air exerts pressure, it exerts force and therefore pressure in all directions. So let's think about the pressure that it's exerting on the wall of the balloon. And here you have all these normal forces of air in all directions. And again, it's the force divided by the area. Although solids, as I said on the previous slide, solids can exert pressure as well, just as they exert forces. And so you look at this cartoon drawing and you think about why something sharp like a pin will puncture. So on the right, this person is nailing a nail into the wall. He whacks it, he applies a force. The nail applies a force to the wall and it goes in because the pressure that it exerts. Now, he can do the same thing with the same amount of force with this bowling pin, and the bowling pin does not go into the wall. Why not? Because it's exerting the same force, but the thing is, the bowling pin exerts much less pressure because the pressure is the force, which is the same as that of the nail, but divided over the area. It's spread out over a greater area, and so it doesn't puncture in. You can press your hand up against a wall, like not a concrete wall or a brick wall, but just drywall. You can press your hand up against it and your hand doesn't go through, but you can apply the same force pushing a thumbtack through and it will go through. And it's because the force is spread out over a smaller area, and that means it has a greater pressure. You can look at these two pictures side by side. We have a brick lying on a soft sponge, and if you set the brick upright, as you can see on the left picture, it has its weight, but it's divided over a small area, which means a large pressure, and it squishes the sponge down. But if you turn it on its side so there's more area, it's not going to squish the sponge down as much because it's not exerting as much pressure. As we think about pressure exerted by a fluid, force divided by area measured in pascals, I want you to know that 1 atmosphere, this is by definition air pressure at sea level. And so 1 atmosphere is a pressure of 1.013 times 10 to the 5th pascals. And I'd like you to remember that quantity because you'll be using it quite a bit in this chapter. And if it's 1.013 times 10 to the 5th pascals, we can also say it's 101.3 kilopascals. In English units, it's 14.7 pounds per square inch. Let's look at problem number 14 in the back of chapter 15. It says, what is the weight of a column of air with cross-sectional area 1 square meter extending from Earth's surface to the top of the atmosphere? So the idea here is there is a column of air directly above you, and that's what causes air pressure. We'll talk about that in another video. So the weight of all that air, roughly 60 miles of air. And let's remember that 1 atmosphere is 1.013 times 10 to the 5th pascals, otherwise known as newtons per meter squared. We're going to use our equation that pressure is force divided by area. And in this case, we already know what the pressure is. We know what the area is. We want to find the force. And the force is the weight. Just like in the previous slide, the brick, the force it was applying was its own weight. So we're going to say that force equals pressure times area. And remember, force is the weight we're solving for. So weight is 1.013 times 10 to the 5th newtons per meter squared times the area that the question asks about, 1 square meter, and we get 1.013 times 10 to the 5th newtons. Now let's put that in units that we can better understand, because we in daily life, most of us aren't used to dealing with newtons. Let's get that in pounds. The conversion in the front flap of your textbook shows that 1 pound is 4.448 newtons. And so we'll do that conversion, get it to pounds, 22,600 pounds, which is about 11 tons. So 11 tons of air straight up sitting over a square meter on the ground. That is it for section 15.1, density and pressure. Have a great day.